All right, so we are looking at the solar system, and we're doing a quick review of the solar system and the solar system data table on page 15 of the reference tables. So I love this picture, but of course this isn't really what the solar system looks like. We're going to talk about how it's impossible to draw any pictures of the solar system that are accurate, because in order to show all of the planets together, even if they're orbiting the sun, you have to make them way bigger than they are actually. The distances in space are so big. So let's start with what's in our solar system. So, of course, solar, the sun. It's the one star in our solar system. The planets, there are 8. And if you still want to count Pluto, then there would be 9. They declassified Pluto. It's now considered a dwarf planet as opposed to a regular planet. Many of these planets have moons. Our Earth has 1. Other planets have many, many more. And asteroids, meteors, comets, other debris, dust. So here's another inaccurate picture of the solar system, showing the planets too big, the sun too big, the dust and the asteroids in this asteroid belt, and also showing the orbits. So these blue lines that circle around the sun show the way the planets are moving, but they're not actually there. In outer space, they're invisible. This is a close-up of the asteroid belt, what these like rocks floating in outer space are called asteroids, and there is a cluster of them between the orbits of Mars and Jupiter that we call the asteroid belt. So quick definition: planets, to be a planet, it has to orbit a star like our sun. Moons orbit planets, on the other hand, so our moon orbits the Earth. An asteroid is a large rock that orbits the sun. A meteor is a small rock that enters Earth's atmosphere, what we know as a shooting star. When it burns up in the atmosphere, we see it like a shooting star. It's, of course, a rock that's entering the Earth's atmosphere. We call it a meteorite when it actually lands on the Earth's surface. And a comet is made of ice and dust, and when it gets closer to the sun, that ice sort of burns off and it leaves a tail. The tail always points away from the sun, no matter where it is, as it orbits. So here's a picture showing the planets in order: Mercury, Venus, Earth, Mars. There's the asteroid belt: Jupiter, Saturn, Uranus, Neptune, and Pluto, and the Kuiper belt way further out. Again, this diagram is not to scale. All these planets, though the planets look like they're sort of the right size compared to each other, they are way too close together for this to be an accurate picture of the solar system. Beautiful, though. So what keeps the planets in orbit? Well, the planet wants to keep going straight. An object in motion stays in motion. So the planet's velocity is this red arrow. So these red arrows show that the planet wants to keep going straight. However, the gravitational pull from the sun is holding it in orbit, it's pulling it towards the sun. So when those two arrows combine, it ends up in a circular path around the sun, what is labeled as resultant path in this picture. So let's talk about some things we know to be true, some Earth motions. Earth rotates once every 24 hours. Rotation makes it look like everything moves around us. So that produces day and night, sunrise and sunset. The moon also rises and sets, so it actually also appears to make a circle around us. And the stars. Sorry, let's see if we can finish this in time. The stars aren't actually moving, we are. So our rotation causes it to appear that all these other things move. So the general rule is if it happens in a day, it's caused by rotation. In this picture, you can see the time zones. This line right here would, of course, be sunset. The east coast is at nighttime and the west coast is still in the daytime. So the sun is moving this direction across the surface as the Earth rotates, causing day and night. Earth also revolves around the sun every 365.26 days. That extra 0.26 adds up to every 4 years we have a leap year, February 29th. So here's the general rule. If it happens in a year, it's caused by rotation. So seasons, for example, most common example, throughout the year, the tilt of the Earth's axis causes different parts of the Earth to get more intense sunlight or less intense sunlight, causing summer and winter. If it happens throughout the year and it changes throughout the year, like seasons, then it's caused by the Earth's revolution around the sun. Another thing that changes throughout the year is we actually see different star constellations, different star shapes. So you might be a Capricorn and your friend might be a Libra, and those 2 times of year are different. Well, those constellations appear at different times of the year. So that the constellation differences are caused by Earth revolving around the sun. As Earth revolves, a different side of it is in darkness, and so we see different stars. So the 2 motions, rotation is spinning around an axis, revolution is orbiting another object. All of this information can be found in the solar system data table in your reference tables on page 15. So pause the video, get out your reference tables, open to page 15, and look at the bottom of the page. You'll find a data table that looks like this. So pause. And welcome back. So you'll see in the left-hand column the celestial object. So the celestial object is the actual thing that's in space. So starting with the sun, then the 8 planets, and ending with the Earth's moon. So for the purposes of this review, we're going to block out this column that says eccentricity of orbit. We're not going to focus on that until we learn the material in next week. So that's why I'm ignoring it right now. The first column tells us the distance to the sun. It's called the mean distance to the sun, which is a mathematical way of saying the average distance to the sun. So for each of the planets, you can see their distance from the sun. Be careful, that unit is in millions of kilometers. So Earth is 149.6 million kilometers from the sun. That's really, really far. The next column shows the period of revolution. The term period of just means the time it takes. So the period of revolution, the time it takes to revolve. So for Earth, there's our 365.26 days. Be careful with this one. The unit is days and years. So Mercury is the shortest, going out to Neptune, which is the longest period of revolution. So that's a relationship. The farther it is from the sun, the longer it will take to revolve. The next column is the period of rotation, the time it takes to rotate. So for Earth, just under 24 hours. The equatorial diameter is a fancy way of saying the distance across the middle, the distance across the equator, the diameter. And that is in kilometers. The mass is the next column. The mass is in Earths, so they've set Earth equal to 1. So if Earth were equal to 1, what would the other planets be? You can see that Mercury is tiny, 0.06. You can see that Jupiter is much bigger, 317 Earths. And then finally, you can see the density in the final column, the density of each of the planets. And, sort of a fun little fact is that Earth is the most dense planet. So the Regents loves to ask questions about that solar system data table. The last thing I want to go over is that there are 2 types of planets. All of these can be found in the solar system data table. There are the terrestrial planets and the Jovian planets. So this is not on the actual table, so you need to know which ones are which, but then you can use the table to figure out all the other interesting stuff about them. Terrestrial planets are the ones that are like Earth. So if you look at this diagram, you can see that Earth is clearly smaller, on the smaller side. And so the other smaller planets are Venus, Mars, and Mercury. For the sake of this, we're going to ignore Pluto. So the terrestrial planets are the Earth-like ones. The other planets are what we call the gas giants. They're much bigger and they're made of gas. So there's a few key differences. The terrestrial planets are made of rocks. The Jovian planets are made of gas. Because the terrestrial planets are made of rocks, they're more dense. The gas giants, the Jovian planets, are less dense. They have much lower densities. You can find that in your chart. And they have different locations in their orbit. The terrestrial planets are all closer to the sun, and the Jovian planets are all farther away, therefore having different periods of revolution. This chart highlights some of the major differences between them. We do not need to know in as much detail, but I thought it was sort of fun. So terrestrial planets are close to the sun. Jovian planets are farther from the sun. The terrestrial planets are smaller. They have a higher density, whereas the Jovian planets are larger, they're made of gas, and they have a lower density. So feel free to take a look, and if you have any questions, please come see me. Make sure you're able to read the solar system data table on page 15 of the reference tables.